Perfect. Thank you everyone for joining me today in this talk, and of course, joining the data engineering community. It's good to see the community here in general. Today I'm going to talk about Apache Hudi and kind of building Lakehouse architecture with Hudi. Before that, like how many of you here have worked with lakehouses or are building lakehouses or the infrastructure around lakehouses, like maybe kind of a gauge in general? Okay, I see some people here. Okay, so yeah, pretty much like you're getting into the journey in a way and like kind of excited to hear about lakehouses. So Hudi is basically one of this lakehouse platform. It's an open lakehouse platform. And I'm going to walk through some of the reason how Hudi started in the first place back at Uber, and what it is basically doing today in today's data engineering world. Like I said, my name is Dipankar. I'm currently a staff developer advocate at a company called 1.0 We build Lakehouse platform, so that means the journey to Lakehouses should be a little bit more easier, frictionless. That's what our focus is. My early involvements have been with like projects like Apache Iceberg, 2021, 2022 time, Apache Arrow as well at the same time, and quite recently I'm focused on Apache Hudi and Apache Stable. So pretty much open source journey here. But in the past I have held various roles in engineering and development in companies like Otis, Dremio, and Click. So in terms of the agenda, we'll start with how Hudi kind of originated. Then we'll do an architectural deep dive. We'll understand some of the reasoning behind why Hudi was even needed in the first place. Then we'll go through how we're thinking about the next phase for our Lakehouse with version 1.0 and beyond. And we'll kind of finish up with some adoption stories just to give you some fuel over there. So let's kind of take a step back to understand how Hudi started, because the problems that were seen back at Uber, obviously Uber was in a hyper growth mode at that point of time, and they were moving from a data warehouse to a data lake environment, right? And you can understand the scale of Uber in that scale. And the problem was whether you have cloud object storage, whether you had an on-premise Hadoop file system, it is an immutable storage system, right? So that means if you have to do a particular update to a particular table, that is your Parquet file, it needs to be rewritten, right? So it's kind of like you have to put a database layer or transaction layer on top of your data lake. So basically data lakes are just storage system, right? So it can be a storage system like S3 or any kind of on-premise system like Hadoop. So there is no storage engine part to it, so that means that you cannot really run your transaction with those guarantees, okay? So the problem Uber ran into specifically was with their trips database, and the trips database basically in a more simpler term, they collect all this information around the trips. And like everyone else at the time, they were kind of doing bulk ingest, and that process basically took them like 120 terabyte, while converting from the old format to Parquet, and then they would do a full recompilation of that format again, right? And so the end-to-end data freshness kind of led to like 24 hours, which leads to stale data, stale insights. It kind of impacts their journey with analytics overall as well. So they noticed their ingest was kind of slow, was really bad, with a lot of reading, writing involved, like I/O and compute spend in that part. And they basically had, these are like really massive jobs, right? If you come from the Hadoop era or like the kind of MapReduce Hadoop era, like running this Hive, like massive Hive jobs is like really cumbersome in a way. Plus there is no guarantees, right? There is no concurrency control like a database system. So what if like two multiple writers are writing to the same table at the same time? What kind of happens during that time, right? No atomicity guarantees. I mean, Hive did promise us some atomicity in a way, but if you have worked with Hive, you probably have a better idea of what I mean in a way. But that was basically the basis of how Hudi started, right? And as you can imagine, like these are much more complex problems to solve, than just purely open table format. And I'm going to discuss a little bit more about, you probably might have heard terms like open table format, open lakehouse, but I'm basically trying to kind of break it down and how Hudi kind of distinguishes from these other table formats in general as well. So when Uber started to tackle this problem, they realized they weren't facing a completely new problem, right? I mean, pretty much all the database system at that point of time, they dealt with these challenges, right? It is just that they needed to figure out how to implement these in a way that kind of aligns with the data lake architecture, right? Going from that transactional database system or analytical database system. So essentially what they decided was, if they could build a system that could be capable of handling these upserts, like updates, deletes, more faster ingestion, then you can basically absorb these changes faster, right? And that means you can do your more analytics faster. And while you're able to do those faster updates, can we query those snapshots consistently, right? That means can you query the latest state of the data that is on your data lake, right? And that means that we are not looking at any dirty data, any kind of zombie data. That means the data that you don't expect in general. Plus the ability to look back at time at a certain point in time, right? And do things like time travel, and do kind of this financial analysis that you would typically do with time travel use cases, right? Like end of quarter analysis or like end of certain financial quarter analysis. So that basically was like kind of the starting point in a way, and ultimately all of these things kind of like led to some of the guiding principles around Hudi. For example, like upsurge was really critical with Hudi. We want to absorb these changes faster, and we want to process this record faster. Incremental read is something very unique to Hudi as well, and I'm going to talk a little bit more about that. But the whole idea is that instead of, I told about the problem statement, right? Instead of doing a recomputation again and again, we just want to consume these changes that has only the changes that has been made, right? Which means we are involving like less compute, that means less money, and less overhead in a way. And finally, snapshot isolation obviously is critical. We want every reader, every writer to kind of like understand the latest state of the table and be consistent with that. So once Hudi had all these abilities, like ability to do things like transactions and upsurge and all those things, the resulting architecture was basically like a database abstraction, but for the cloud object storage or any kind of like on-premise object storage, right? So now we have faster upsurge, different kind of indexing scheme is built with Hudi, which is very core to like any kind of database system, but we are trying to bring that with the data lake and data lakehouse environment. And you can incrementally build these tables. So for example, instead of ingesting like 120 terabytes of data, every 8 hours with Uber, they could now just upsurge a few gigabytes of data, right? Every 10 minutes. So that makes for really efficient downstream ETLs. And Uber actually builds most of their core warehousing tables in this incremental fashion, where they process only the incremental changes every few minutes and then they execute that. This is not as ubiquitous as we would like it to be today, but we focus on that aspect a lot with Hudi, with incremental processing. All right, so this is probably one of the slides that should give a better idea of why a lakehouse and what are we thinking in terms, and there are a lot of multiple things here, but I'm going to keep it a little bit more simpler here. So basically, a lakehouse, if you consider the term itself, right, you consider a lake and a warehouse, that's a common jargon that you pretty much see in all those blogs and stuff. But the whole idea is basically data warehouse has great data management capabilities, right? Things like compaction, clustering, and ability to do things like schema evolution, right? You make some changes to a particular table, how easy it is to evolve that schema, right? Things like time travel I talked about. Then there are things like ACID with guarantees, right? You want to do all those things with ACID guarantees so that everything is consistent as per you would expect. So a data lakehouse basically builds on that idea, and it kind of brings that the best part of data warehouse, which is the data management capabilities, but also the scalability and the cost angle of data lakes, right? So data lakes are great with scalability, right? You can basically scale as you want, and there is a cost aspect towards that for sure, but it's still cheaper than you would expect from other like on-premise systems. So that basically led to kind of the inception of the lakehouse architecture, where you're kind of bringing like the transactional capabilities from a data warehouse, like a database, and bringing that to a data lake, which actually doesn't have any transactional capabilities, right? So if we talk about the components, if you see here, I'm going to start with the bottom part. There is a lake storage, and I would highly recommend comparing this to any kind of a database system where you have their own storage, right? So this could be, again, your Amazon S3 or Hadoop file system or any kind of like object store. And a layer above that, you will see the file format. This is where your Parquet file is, ORC file. This is where your actual bytes are written, right, to that particular record. The layer above that is basically the open table format layer, and I mentioned Hudi there, but obviously there are other formats in general as well, like Iceberg and Delta Lake as well. And there are other formats like, we are going to hear about Lance today as well, but there are some other formats coming up as well. But that's just a single component of the entire lakehouse stack that you see here, right? It's just one single component, that's the metadata layer. So basically the data layer is the file format, and the metadata layer is a layer above that, which is the table format. So if I have to like really break it down in a more simpler term, the table format is nothing but just metadata about the files that are in your storage system. Now the layer above that is basically very unique to Hudi, and is one of the like robust thing that kind of like makes Hudi more like faster in terms of like ingestion, performance, and all those write capabilities and all those read capabilities. And the thing that I typically compare this is with any kind of database system. For example, like if you have worked with a system like MySQL, they have their own storage engine as well, like InnoDB, like MyISM. You can really plug in those systems and you can like take advantage of certain things that one doesn't suffice, right? So storage engine, if you see kind of like literature of any database system, you will understand that storage engine basically has things like access control, like indexes, right? Concurrency control techniques, right? How do you tackle like multiple writers writing the same table at the same time? Then there are table management services, which is also very important because you can build your Lakehouse pipeline and you can build your Lakehouse architecture in a way that suffices your like needs and stuff. But the main part is how do you optimize those tables? How do you keep your storage in check, right? Because that's where you're going to end up with a lot of like performance thing. Ultimately, your compute has to read from the storage system. So if you have more files in your storage system, that means you're reading more number of files, which means it's it's kind of linearly grows in a way, right? So the storage engine is very unique to Hudi. Hudi kind of naturally embeds that as part of its own Lakehouse platform. And there, if you see a layer above that, you will see the different writers, readers. On the right-hand side, you can see different catalogs. That's how you're making this data from your storage system available to this different kind of system, like whether it's your Spark, whether it's Presto, Trino, or any kind of compute and analytical tools, or your machine learning pipelines. The one other thing on the left-hand side for Hudi, which is the platform component, is also very native to Hudi. Basically, Hudi also brings other services like ingestion services, which are heavily used in production, like there's something called Hudi Streamer. Then there are catalog syncing services, which makes it super easy to basically sync your tables to your different catalogs, different readers and stuff as well. And there are some active works that are being done as well, like timeline meta server. The idea is to basically kind of like accelerate your queries. So there's some work going on in the meta timeline server as well. So that is basically the open Lakehouse platform of Hudi, and typically any Lakehouse architecture will have the same components, like you will have the storage, you will have a file format, table format, or whatever it is, and you will have a reader and writer, right? Now, the way I see it, and when I was kind of beginning my journey into the Lakehouses, I came from a data warehouse and I was working with data warehouses, right? So I actually published a paper about how a Lakehouse compares with a warehouse. Basically, the whole idea is that you have the exact same component in a data warehouse as well. If you take any kind of warehouse, like Snowflake, for example, right? The only difference that kind of like stands out is that all of these components are very modular in nature, which means you have the flexibility as a user to basically plug in the things that you would like to. And by that, I don't really mean like you have to build all of this yourself. Like I said, like there are platforms to do that as well that does this thing for you. But if you want, the choice is yours, the flexibility is yours, right? So this means you are not limited to only a particular set of compute engine, right? For example, if you use a particular proprietary warehouse, you have to only store the data in their storage. You have to use the compute of their particular platform. So this means we are making data as an open and independent tier, and that means it's available to any kind of engine that kind of supports that particular format, right? So that is the kind of main difference between any kind of a database system or like a warehouse system versus a lakehouse, where you have the flexibility and the openness. And that's why the open part of that. So this is what basically a lakehouse architecture would involve. Now I'm going to deep dive a little bit more into the table format component of Hudi and see how basically that is laid out in a distributed file system. So basically, the whole idea with Hudi is something called the concept of file slice and a file group. So basically, a file slice typically consists like a base Parquet file, which is like a columnar file that you typically use for analytics. And for certain tables, which I'm going to talk about next, like merge on read table, there is something called like log file. This is where you store only the updates that has been made to a particular table. Okay, so these two components, like the base Parquet file, the log file, they together we call them as a file group. And whenever a record comes in, let's say you're inserting some new records into a Hudi table, right? So Hudi will basically write those records into these file slices, and ultimately each record has a key, which kind of like is a primary key in a database system, and that is mapped to a particular file group, and that file group would never really change. So that actually helps you to like really understand, because imagine the scale of your storage system, right? You will have multiple Parquet files, you will have multiple like tables in your storage system. So how does your engine really understand where a particular record is there in a particular Parquet file, right? So the whole idea is to basically easily figure that out, and the way to do that is basically like tying the primary key to a particular file group, and that assignment will kind of like bring that out in a way. Now, before even going back, diving deep into the bottom part, like the two important things that I would like to mention here is the timeline, which I'm going to talk in the upcoming slides, and the other thing is the metadata table. So since we have talked about Hudi tables in general, and I talked about this file group and file slices, I think it would make sense to understand what are the different table types in Hudi. And typically these table types have also been used with others like file formats or table formats like Iceberg and Delta Lake as well, which is copy on write and merge on read. So with copy on write, the idea is basically, like I said, these Parquet files are immutable files, right? So that means any update that you make to this particular file, they have to be rewritten, right? It's an immutable file. So copy and write basically takes the base version of the Parquet file and it rewrites a newer version of the Parquet file, right? Now, one thing to understand that is because of that, we are actually going to end up with a higher write amplification because you're rewriting that entire Parquet file again and again, right? Which can be super costly and time consuming if you consider the scale and the type of workloads with Lakehouse. With merge on read, the idea is slightly different. I talked a little bit about that. We talked about the idea about having that log file along with the Parquet file, right? So with merge on read, we are not rewriting that Parquet file again and again. We are basically storing all of the updates in a particular file called log file, and we are deferring that ability to merge that particular two files towards the reader side or towards a particular table service called compaction, which basically merges these two different things. So the one thing to understand here is that we are basically balancing the read and the write amplification here. So now the read overhead is slightly higher. Obviously there is an operational thing here that you have to merge this to Parquet and the base file because you want to get the latest state of the data, right? So what we're playing against is basically the freshness of data versus the performance of it, right? So if you want your data and insight to be fresh, yeah, go ahead. Hudi will do is inline asynchronous compaction. So as your ingestion job, right, make those updates, it will in the background compact those files, and that will make it available. So that's pretty much the difference. And I just put up a faster comparison slide just to give an idea. The write cost obviously is higher with copy and write. I talked about that. With merge on read, it's a bit lower. On the latency side, copy and write is obviously slower, but merge on read is faster. Query speed and overall cost-wise, I would say obviously copy and write, there is no read side overhead, so that it's faster. But overall cost-wise, copy and write could be a little bit aggressive. So the use case to think about that is basically when you have let's say some streaming-based workloads, right? The idea with streaming-based workloads is you write the files as soon as they arrive, right? That means writing it in more smaller chunks, which means you can have a lot of this kind of smaller files. So with merge on read table, that's a really good use case for streaming-based use cases where you're trying to merge these different kind of files, and it kind of involves writing at a faster pace because all of this merge activity is paused towards the read side. So that's kind of the idea with merge on read and copy and write. All right, so basically we have a good idea in general as of now about why Hudi and how it started and the kind of the architectural deep dive in a way. Now let me walk you through how we are kind of envisioning Hudi 1.x, 1.0 and beyond. Basically the way we see it is kind of a database for the data lakehouse, right? So the good thing is with Hudi, on the right hand side, if you see that's basically a Hudi 1.0 RFC that I pulled up from GitHub. And this is a very seminal database paper. If you are from a computer science background, probably have came across this paper called Architecture of a Database System. So if you compare these two pictures, you'll pretty much see that a database system and Hudi has similar components. As you can see, there is access control, there is this buffer manager, there's this log manager, this is log manager, which is pretty much the stuff that you see also here in the transactional store manager in Hudi. Now the yellow stuff is where we are working right now with a lot of focus on this particular areas. But pretty much all of these things are already there. So the building blocks are there. We're basically kind of building a database for our lakehouse architecture. The one thing to, So the one thing to kind of introduce here is the timeline that I kind of paused, during my kind of Hudi deep dive format deep dive talk. Basically, timeline is something that we kind of are redesigning with our new kind of format. So just to keep it short, timeline is basically kind of the heart of the Hudi table. So every action that you kind of do in a Hudi table, whether it's a commit, whether it's a compaction job, a clustering job, everything is recorded in a timeline in Hudi. And that kind of serves as the event log and kind of a basis for all of this transaction, right? So the timeline records every change that are made, and essentially it powers all of the important things that you see with Hudi, like ACID guarantees, ability to do things like non-blocking concurrency control, and advanced capabilities like incremental processing and stuff. So really, if I have to think about the heart of Hudi, the timeline is the heart of Hudi. And the idea with the timeline was initially we had the concept of the active and the archive timeline, because as you can imagine, as you are writing more commits, your timeline can really grow linearly, right? So that can be super expensive, as you kind of like grow the timeline with more kind of like activities, more kind of like updates happening. So we basically had the idea of active and archive timeline, and active timeline basically had a limited log history. So we kind of like flush all of this, archive things towards the archive timeline. So that means we only access the archive timeline whenever it's needed. For example, like for timetable use cases, right? For example, you want to go back and read a particular timeline of data. That's when you will actually call the archive timeline. So that's kind of the difference between the active timeline and the archive timeline. Now, what are we changing with this? There was certain limitation in general, and we're also thinking about some newer use cases. So basically, what we're introducing here with Hudi 1.0 is a LSM-free timeline. Again, for people who are from computer science background in general, probably have an idea of LSM-free timeline. And especially how it works is basically, we organize these different files in different layers, like levels, like level 0, level 1, and following a kind of log structured tree like style timeline. And what we are basically doing here is each file is a Parquet file that you see in the orange here. And each of these files, they store a particular batch of timeline instant, right? And their metadata are actually stored, kind of sorted chronologically by timestamp. So we basically kind of like arrange them in a particular like timeline order and following a particular naming convention. For example, in the first level 0, you see it is 101 to 110, and then you see until 200, right? Now, once we particularly kind of like deal with a particular level, we also like compact that particular thing and flush it to the next level. So that means it kind of like gives an ability like to kind of like keep the top level things in the memory and the remaining level efficiently for kind of from the disk you can pull it up. So that means it's less expensive in a way. And that also helps us to kind of manage all of this thing that I talked about, like the timeline, right? How it can grow very linearly and how it can become like super expensive as such. Also, we are trying to like unlock some other use cases here, like for example, like infinite time travel, non-blocking concurrency control is something that I'm going to talk about next, but these are some important use cases that this LSM tree timeline can basically allow us to do. So yeah, non-blocking concurrency control. So in general, historically, how we have seen data lakes is primarily through kind of a lens of like batch job, right? So the go-to method kind of handling multi-writer scenario. So just a background in general. So why do we even need concurrency control? So concurrency control, imagine it's like a traffic police, right? You have multiple cars going at in the same lane. How do you kind of manage that particular thing, right? With this lakehouse architecture and data lakes in general, and obviously any kind of data system, we want to make sure like, the right writer has, or the right reader has the right access to the right set of version of tables and the right snapshot and stuff, right? So typically what we do is we basically like use something called optimistic concurrency control, which is OCC. And this is what, so the whole idea of optimistic concurrency control is you assume that conflicts are very rare, right? And you proceed based on that. And what happens is during the commit time, when their conflict arises, you actually like fail that particular commit and you have to retry that commit again, right? So that basically is the idea of optimistic concurrency control, and that's why we are calling it optimistic and not pessimistic. So the one problem that you typically would kind of like face with the lakehouse architecture specifically is because conflicts are not really rare. You will have the whole idea and the premise of the lakehouse is that your data is open. That means multiple compute engines are going to access the same set of data from the same table, right? So when we are saying that, that means we are assuming multiple writers to actually interact with the table, right? So we cannot really assume that conflicts are going to be rare. It's going to be not rare. Especially in real world scenario where like things like GDPR purges, right? Where you're kind of trying to do GDPR deletes or backfills and those kind of stuff, conflicts are not really rare. And most implementation today, they check for overlapping like kind of file changes at commit time. And if overlap is found, like I said, they fail the entire job. Now, what happens is that these are massive jobs, right? You're using a lot of compute, there's a lot of money involved in general, and there are a lot of resources in general. So if you have to like fail a particular job, that means you're basically wasting that resource cycle, and you're also like spending your money in general. So if you see the diagram here, you have a particular ingestion job running, right? Every 30 minutes that's running. But there is also a long-running delete job that, let's say, fails here, right? A particular commit fails here, right? Now, what happens is you retry that particular commit because you are optimistically moving ahead. But then at some point in time, it again fails again, right? So that is basically a starvation issue that we generally say, and we are trying to avoid that starvation issue with other concurrency control technique. So while OCC kind of gives us a starting point for isolation, it's not always sufficient for kind of high contention, high concurrency kind of workloads. And that's where Hudi kind of like has a different kind of like way of dealing with that. Hudi actually introduces 3 different concurrency techniques. One is the OCC, which is optimistic I talked about, NBCC, which is multi-version concurrency control, and there is something called non-blocking, which is basically what I'm setting the premise for the next slide. The whole idea with Hudi is that you actually distinguish different actors. Like, for example, there is a writer, which basically writes into this table. There is a table service, which basically like does things like compaction, clustering, and all this kind of like table management thing, right? You want to manage those tables. And there is the reader, right? There is the analytical side thing. For example, your BI dashboards, your machine learning tools, or whatever system it is, right? So these are the readers. Now, Hudi distinguishes between these different actors so that you can understand what's really going on, right? So it implements OCC between these writers and provides kind of relation semantics in a way. Between the table services, it's multi-version concurrency control. So each of these kind of table services like compaction and clustering, they can actually work with the ingestion writer at the same time in the background without really interfering with each other. Like, imagine what would happen if you would not have such a service. Like, for example, like, just to give an idea, like compaction or clustering is basically table management services that are basically used to optimize your data, right? Now, if you don't do that with your writers, your storage system is going to be piled up with a lot of files. It can be less organized, right? You know, for example, you query by a particular state, but maybe that particular state data is across a lot of Parquet files in the storage system, right? So that means your compute engine actually has to go and look for each and every Parquet file in its different kind of like, in your file system, right? So that means you're wasting a lot of time, which is like related to your cost and your money and everything around that, right? So basically NBCC kind of like works between writers and table services. Non-blocking concurrency control, I'm going to talk a little bit more about that, but that the whole idea is to not block anything. And finally, snapshot isolation blends everything together. So that means every kind of actor, like reader, writer, everyone kind of gets to see the kind of latest state of data. This is the internal diagram of non-blocking concurrency control. But what I mean to like explain here is basically like the whole idea of NBCC is that multiple writers can write to the same Hudi table concurrently without locking and without having to fail. That's really important, right? Instead of blocking writes, Hudi allows them to like proceed in parallel, and what it does is it actually defers that particular process of like conflict check during the time of query like reading or like services like compaction. So you're basically like trying to like put that conflict check in a later phase, right? Now NBCC uses some minimal log in the background, like to just write the commit metadata, but basically that ensures like a global serializability and global local guarantees, which ultimately make sure that data is very consistent in a way, right? And all of this is done by something called true time semantics. If you know about Google Spanner database system, if you read the paper, they actually introduced the true time semantics. So the whole idea is that now in the timeline of Hudi, we talked about the timeline, you have a kind of a requested time and a completion time, right? And these particular requested time and completion time, they act like interval. With the interval notion, we are trying to gauge a little bit more idea of how we can like proceed different writers at the same time, right? That's what basically kind of gives you like the idea of like multiple writers proceeding without blocking anything. I'm going to leave some blogs later on for the community as well. I recently published a lot of blogs around concurrency control and non-blocking and how it kind of helps. So I'm kind of walking in a more faster pace, so I hope you can have a detailed look on the blogs later on. Indexes. Indexes is another important thing that is very like core to Hudi. Like the whole idea of indexes, like you probably are aware of, like in any data system, is that you want to use the index to kind of understand where a particular record is. That means you are able to reduce the I/O cost and kind of improve the query performance. So Hudi actually started with index in the first place, like from like right from the day one when they kind of like open source that. And as you can see in this particular diagram here, like with index. You can see there is the merge cost is like 600 MB. Without index, the merge cost is 1200 MB. The reason for that is Hudi basically uses this indexes to find out where exactly you need to merge this update. So let's say you are running an upsert query or update query, right? Now Hudi or any kind of like table format, they need to understand where in that particular record is there in the files, right? And to do that, Hudi keeps a track with these indexes that basically helps you to like get more faster access to record, so you know where to write those records more faster. And obviously Hudi has different type of indexes like Bloom filters, like HBase, record index, and all those different kind of indexes. But with Hudi, like one thing that we kind of also develop is like a multi-model indexing system in itself. So it's like an indexing subsystem, but it has all of this like file statistics, right? You want to like read the statistics from a Parquet file to understand what is the highest value and the lowest value. There are column partition statistics, there's Bloom filter, record index, and now with the newer version, we're also introducing like the expression index and the secondary index. Quickly, just to explain what is expression index. So basically, you can create an index on a function of a particular column, right? So it's like simple as like create index timestamp hour on Hudi table. Now the example to like kind of understand that, let's say you have a timestamp column in your table that is basically like holds like epoch timestamp, right? So users might now want to filter or query the data by hour, right? So in that case, in the previous world with Hive, we used to have a different like partition column in there, so that's really cumbersome as well. With this index, you're basically like trying to create a function of that particular timestamp column, so you just do a function of hour, and that means your users don't have to know about anything about that, and you can just query that thing directly from Hudi tables.
From the original table?
Yes, from original tables, perfect, yeah. And the similar thing with also secondary index, right? So the idea with secondary index, as you see with any database system, is that it's kind of an index on non-primary key. And Hudi basically like recently released this particular secondary index so that you can create a second index on this non-primary key, which actually relies on this primary key to kind of figure out this particular set of record from the Parquet file. So that's another innovation which is completely new to the Lakehouse space in general. All right, so I'm at the end of my talk. I just wanted to share some few stories, like just to get some fuel going on there. These are like some of the recent stories. Obviously, like there are other stories I would highly like ask you to like visit our website, which is like hudi.apache.org. We also have this published as blog, so you can read these stories, you can understand what values this kind of companies gain from adopting Hudi. One recent story was with Amazon. Amazon's selling partner services data engineering team, they actually are responsible for kind of handling seller-side data. And one of their main kind of metric is kind of contribution profit, so it allows them to like do things like pricing, forecasting, running some ML models and stuff. So basically they adopted Hudi to kind of like deal with the challenge, and the challenge was supporting this kind of scale and diversity of use cases, more faster updates and stuff, and that's what kind of Hudi helped there. Uber, obviously like Uber has been like with Hudi with a long period of time, but this particular team, they actually are dealing with like things like trips with Uber trips, like or like Uber Eats kind of delivery tips and stuff. So you have all this late arriving data, right? You update you kind of update order something and you tip your particular order. So that particular tip comes at a later phase in time, or your driver kind of like gets the money in a later point of time. So that basically was one of the challenges, that how do you handle this kind of late arriving data, and Uber's Lakehouse journey basically took that. And here are two more examples. Notion, you probably are aware of Notion now, like it's kind of like a workspace in itself. They have been like dealing with a lot of cost problem in general with the data warehouse. And they migrated to Hudi, and they still have some of the workloads with Work Warehouse, but with Hudi they're able to save a lot of costs in general by migrating these workloads and running faster updates, CDC pipeline and stuff. Peloton is another example, and it also like has a similar use case, like ingestion frequency is like super high, the cost saving is super high in general as well. So these are again like pretty much like available as blog. I can share them later as well, but thanks to the community, like with the Hudi community from back in 2016 started, and we have a diverse set of committers now, PMC members, different organizations, different teams contributing to Hudi. We have a Slack channel. You can scan this QR code if you are interested in general about Lakehouses or you want to be updated with the community. I would highly appreciate joining. We also have a couple of social pages in general. But yeah, I mean, feel free to like, if you have any question in general, I'm happy to take that, but I'm also available in general for networking, so I'm happy to chat. Thank you so much. Yeah.
Do you want to take questions?
Yeah, if you have any questions, I can take that.
Did you have one? Great presentation.
Thank you.
Can you, you mentioned the part about the raw ingestion stream, and then you're managing this, Hudi's managing the kind of like the storage of that.
Right.
But the raw input stream, Hudi doesn't control how that writes data to the original raw tables. Is that right?
I mean, yeah.
Can you touch on that?
Oh, like, do you mean like from a compute angle or like?
Yeah, well, because those are separate computes, right? They're just writing these. So you don't have any control over how they write the data.
Yeah, but in general, what basically Hudi's storage engine would do in this case is basically like the granularity of your writes. For example, your ingestion frequency, right? How do you balance your ingestion with your compaction of small file? All of this thing basically needs some kind of coordination, right? Because you want to like ingest your data at a faster frequency, but you also want to background, in the background compact the data, right? So those kind of granularity is what basically Hudi's storage engine allows you to do. And similarly, like concurrency control that I talked about, it also like touches around how we kind of like balance that thing with different writers and different compute engines. Anyone else?
Can I have one more question?
Sure, yeah.
That is managed, so I was looking at some of your docs, you manage that through writing Spark notebooks, is how you would kind of do that configuration?
Yeah, the compute can be Spark, Flink, any depending on your workloads, of course, right? But if your question is like where it happens, or is it like
if I was setting that up on my data, like I have a data lake, I have an ingestion stream,
Right,
I'm setting
right,
that up.
right.
Where's my entry point?
Oh, you mean like whether using a notebook or any kind of like an environment? Oh yeah, it can be like a notebook environment, but of course like a lot of people like run Hudi or any kind of table formats with like things like EMR or like Spark-based compute like platforms. Even my company like OneHouse does that thing, like it allows you to run any kind of open engines towards that.
I get you. Okay, cool.
Yeah, so basically you have the flexibility for yourself. Yeah.
Actually, we're quite ready. Basically.
All right. If there is nothing, I'll hand over to Jack. I already took some of his time.
Cool.